So many thanks to the organizers for throwing this together and for inviting me. So it's been great so far, although it's been very short. I only arrived on Tuesday. All right, so so there's been a lot of talks on PDMPs and non-reversible MCMC. So I've got some introductory material, which I'm guessing I can safely skip through. So I'm just going to go quickly. And then I have some results in geometric ergodicity, which are now getting a bit old. They're more than a year old, so they're quickly getting maybe obsolete. But anyways, and then I'm going to go on to talk about scaling and about some stuff I've been working on recently with Daniel, who's sitting just there, Alex Bouchard-Cotet, and Arnaud Doucet. Okay. So again, the framework is the standard one in MCMC. So we want to sample from a target. It takes this form. So U is a potential. The normalizing constant is unknown, but we can compute U. It's a very generic problem. It appears in many places, as you all very well know. So we can skip this. Okay, so PDMPs, if you haven't already noticed from all these talks, they were mainly introduced in physics. So they go back to a paper by Peters and DeWitt. Actually, so they were introduced for sampling, right? So before that, they were studied by Davis at Imperial a long time ago, around the 60s and the 70s, and there's a lot of results from that respect. So they were used for control and for modeling various cues in continuous time and so on. So actually, the nice thing about these is that they sometimes demonstrate state-of-the-art performance in realistic problems, large-scale physical models, for example. So they're quite promising for use in MCMC. So the basic ingredients of a PDMP is basically a deterministic dynamics, which is an ODE. So you have some kind of vector field. You compute the solution to that ODE, and then you have an event rate, which depends on the location. And at those times, when you have an event, you apply a Markov kernel. Okay, so there's many flavors. For example, there's the bouncy particle sampler, which goes back to Peter and DeWitt, and then it was introduced for sampling in stats by Arnaud, Alex Bouchard-Cotet, and Sebastian Vollmer. Maybe not in that order, but then there's the zigzag sampler, which goes back to at least 2012. But so for MCMC, I think the earliest it goes back in the general case of multivariate goes back to this paper by Joris Birkens, Paul Ferdinand, and Gareth Roberts. And there's many more versions, so actually they're quite easy to adapt to your purposes. There's many more versions coming out, so it's quite a lively topic. So again, now I'm going to start focusing on the bouncy particle sampler. So we extend the target by including a Gaussian or maybe a uniform on the unit sphere. And that serves as the velocity, just like you would in HMC. The dynamics are very simple. The location just follows the velocity, and the velocity stays fixed. And this is the event rate. Okay, so far nothing new. The kernel basically is either you do a bounce, which is, as Alex described yesterday, you just reflect on the, with respect to the plane, to the tangent plane of the contours of your potential. But then there is the issue with reducibility. So if you just do that, you can, for an isotropic Gaussian, you will never enter a ball of a certain radius. So to beat that, you can add a refreshment rate at which, so an independent Poisson clock with potentially location-dependent rates. And at those times, you just completely refresh or partially refresh the velocity, and that allows you to go from any point to any point, thus removing the problem with the reducibility, which is very similar to HMC, to be fair, right? So if you just run Hamiltonian dynamics, you will just be exploring one of the contour sets. You need refreshment to add or remove energy, and then to move between different contours. Okay, so I mean, all this is now pretty much well known. So it's invariant and it's ergodic as long as you have positive refreshment rate. So that's all pretty good. Okay, so now the question is whether piecewise deterministic Markov chain Monte Carlo is any good. Does it actually perform well compared to other methods? Why should we bother? I mean, it is in continuous time, it's pretty fiddly to implement, although it does work. You can actually implement it exactly for many distributions of interest, but why should we bother? Okay, so actually what we need is we need some kind of convergence guarantee for their performance. We need to know how they scale with dimension and what kind of problems we can tackle efficiently. And the other thing would be nice would be to get a central limit theorem. Now, the problem that comes here is the non-reversibility. So CLTs for Markov chains and Markov processes are very nicely described for reversible processes. There's many tools you can use. But once you go to the non-reversible case, you can basically, well, you can still use L2 methods, but they're not so nice anymore. You don't have spectral results, spectral calculus, which actually helps you solve a lot of problems very easily. The other thing is that if you go beyond reversible processes, a lot of CLTs and convergence results are based on the symmetric part of the generator. So that is, if you take the generator and you add, it's a joint, you divide by 2, that gives you a symmetric generator, and that's the thing that counts for the Dirichlet form. So a lot of results depend on that, for example, sector conditions and so on and so forth. The problem with this is that the symmetric generator of pretty much all PDMPs that are used for sampling is that it's degenerate. So it only works on the velocity, it doesn't do anything to the location. So as soon as you apply it to a function that is either constant with respect to velocity or it has some kind of symmetry with respect to the target distribution, that will give you 0. So there goes your spectral gap. Okay, so there's no spectral gap. So if you want to get a CLT, then the first thing you could do would be to use geometric ergodicity of the main and Tweedy flavor. Okay, so you just need a Lyapunov function and a minorization condition. So that was the first result I wanted to mention. So PDMPs were a little bit fiddly. So there was a result going back 2010 by Mesquita and España, but it was just for exponentially decaying targets. So it needs to decay like an exponential function. And the process was slightly different to either BPS or zigzag. Also, Pierre Montmarché had results on compact state spaces, and Joris Birkens with Andrew Duncan had results for dimension 1, but under very general conditions. And they had an exact formula for the asymptotic variance, which was very nice. Okay, so I'm going to talk about results we got with Arno and Alex maybe a year and a half ago. Since then, zigzag has also been shown to be irreducible and geometrically ergodic under very general conditions by Joris, Gareth, and Pierre-André Zitt. And there's also a paper by Ninon Fetik about a year ago. Okay, so I'm going to... Okay, still got plenty of time, so maybe I can explain. So these are the conditions you have. Basically, you need second derivatives to be well behaved. You need the gradient to have finite moments, and you just need this. But this is actually, you can get rid of it because it only matters what happens outside a ball of, outside of any compact set. And because we assume the gradient is blowing up at infinity, this actually doesn't matter. Okay, so we treat velocities living in the unit sphere because it makes calculations a lot easier than dealing with Gaussian velocities. Okay, and this is the first result we got, which basically covers all distributions that satisfy those assumptions with growth between an exponential and a Gaussian. Okay, so the potential grows at least as fast as a linear function, and at least at most as fast as a quadratic. And then we've got two different cases. So in either case, we're assuming that the Hessian is that the Hessian? No, yeah, the Hessian. So the second derivatives are bounded at infinity. And so this corresponds to the cases after, so strictly faster than exponential and slower than Gaussian, and this corresponds to the exponential case. So under these assumptions, so essentially the only tricky one is here. So in the exponential case, you need a refreshment rate which vanishes with a dimension. Actually, I'll explain in a moment why that is the case, but it's not necessary, right? But it just it was necessary for the proof to go through. But one thing, one reason you can think this may be intuitive is because if your gradient is constant in the tails, then if you refresh too much, even if you refresh at a constant rate, but that rate is very high, that will start competing with your bounces. And then you're going to end up doing random walk in the tails, which is not a very efficient way to explore. Okay, so, and the Lyapunov function takes this form. So what's interesting about this is that this is the invariant distribution of the jump chain. So if you look at the process just after every event, so exactly after the event, not exactly before the event, because that defines a different jump chain. But if you look just after the event, this is the invariant measure of that Markov chain. And there is a very nice analysis going back to Costa and Dufour. They give you a lot of properties of the PDMP, and they show they're equivalent to similar properties for the jump chain. So then if you look at this, the Lyapunov function makes sense, because it's very often the case that if you're trying to prove ergodicity, geometric ergodicity, the Lyapunov function looks like the density of the invariant distribution to some power of this form, minus a half, minus a third, anything between 0 and 1. Okay, so if you have thin tails, so if your tails decay faster than a Gaussian, then you have very strong potential out in the tails, so that will essentially drive the events, okay? Now, again, this is not a necessary condition, but it's sufficient for geometric ergodicity. But again, some intuition about this may actually be important, is that if your tails grow very fast, if you start tangent to your contour, now you have refreshment rates. So technically you shouldn't have the problem with the irreducibility, because there's a positive chance of refreshing. But if you start with gradient 0, which is the best chance you have for refreshment, because the next event has the highest probability of being a refreshment rather than a bounce, after a tiny time interval, the gradient is so big that this inner product will have dominated any constant refreshment rate. And that's after a tiny time interval h, so we know that events don't happen any faster than that. That's the natural time scale to look for events. So essentially, although there is a positive chance to refresh, that will happen extremely rarely. So that may kind of affect any kind of quantitative rate you want to get. So, a way to deal with this was we decided to introduce this location-dependent refreshment rate. This doesn't actually increase your cost that much, because it grows less than the gradient. So still the bounces will be the dominant effect out in the tails, but you just make sure that you have enough refreshment to make sure there's a chance you don't get stuck on those outside those balls. So so for thin tails we have this result. So we have some conditions here, and then the remaining case is essentially thick tails. Now thick tails are a bit more problematic. We know that essentially many algorithms for thick tails are not geometrically ergodic. And in this case, the problem that appears is that, again, because you don't have enough information from the gradient out in the tails, you're just doing random walk. So the way we dealt with this was to apply it. So this is an approach that was pioneered by Johnson and Geyer. Basically, what you do is you transform the target. There's a very nice set of transformations that you can apply. And by transforming it, you ensure that your target falls in one of the known categories of geometric ergodicity. And then what you can do is you can transform the process back. It will be a PDMP. It will no longer be PS process once you observe it back in the natural parameterization, but you can simulate it, and that thing is geometrically ergodic. Okay? So in all of these cases, you get a CLT, but it's very hard to estimate the asymptotic variance. So the main Tweedy approach actually gives you some kind of, well, it doesn't look nice. It's hard to get any kind of feeling on what's happening. Okay, so More recently, so I mentioned Joris, Gareth, and Pierre-Andre posted very late in 2017 a paper proving that zigzag is ergodic and geometrically ergodic. So that's without refreshment, so that's the tricky part, proving irreducibility. And they use a very fairly natural set of assumptions. And there was a paper by Alain Mouche, Guillan, and Montmarché, again recently, that extends the geometric ergodicity. And they also introduced a coupling for the minorization, which is interesting, may be interesting for other reasons apart from the geometric ergodicity. So in all of these cases, as usually with drift and minorization conditions, except maybe for very carefully designed Gibbs samplers, the small set that you use in the minorization gets small very quickly in the dimension, and that kills your return probabilities. And also, it's hard to control the contraction rate and the drift, so the constant in front of your Lyapunov function on the right-hand side of the inequality. So usually, the rates that you get for the exponential convergence, they decay very quickly in the dimension in a way that actually it doesn't mean that the algorithm doesn't work in the high dimensions. It just doesn't allow you access to any useful rates. So you need different methods to understand the performance in these in high dimensions. So the approach we're going to take, at least for now, is we're going to look at a scaling limit, which is very similar to what Alex described yesterday. Of course, since the end of the previous month, we also have Christoph's paper with Roussel and co-authors, which also gives you another way to study, probably more exact, but bear with me, hopefully you'll find this interesting. So scaling limits were essentially introduced in MCMC by Roberts, Gilman, and Gilkes. Actually, there's another paper as well, which is around that time, but it doesn't study high dimensional cases. It studies something else, but I forgot to mention it. Anyways, I don't even remember the name of the author. So this is essentially now considered to be the first paper in this kind of topic. And so this studied a random walk metropolis. And essentially, you study it in high dimensions, either some factorization assumptions or some weak dependence assumptions. And essentially, you derive a theoretically optimal acceptance probability, and therefore, you can kind of use it to provide a tuning guideline. And it's also been done for the Mala algorithm by Gareth Roberts and Jeffrey Rosenthal, and by Beskos and co-authors in 2013 for HMC. So I'm not sure if there is actually a weak convergence result here. I think it's just an analysis. Are you actually one of the authors of that paper? I just was wondering. But there is a kind of a scaling analysis in terms of the acceptance probability, and I think there is a scaling limit, but it's a discrete time process. Whereas with everything else, with Mala, with random walk metropolis and so on, it's usually a diffusion. Okay, so the usual framework is the following. So you have a sequence of targets. We want to study what happens as the target increases in dimension. A common oversimplified scenario, which kind of makes sense for many cases because it just simplifies the calculations, and very often you can remove this kind of independence assumption by a weak dependence assumption. So basically, this should cover scenarios where the target is weakly dependent. Now, if you move towards a target which has like a non-sparse dependence covariance matrix or dependence matrix, then I have no idea if any of these results actually still make sense and the scalings, but this is the kind of scenario we want to look at. So you look at the Markov chain or Markov process generated by the algorithm you're interested in for each of those targets. You decide on an observable, so usually you project down on the first few coordinates, or maybe you can look at some kind of other observable which looks at all of the coordinates at the same time, like the radius, like Alex did, and Kengo did with Gareth and Joris very often. But in the original papers, usually was the first few components. And then you look at the observable evaluated at the Markov chain. Sometimes you speed up time. So the effect of that is like you're zooming out. So if you plot the process that's generated by that formula, it's like you're zooming out the time direction and you're looking further and further, which is kind of traditional also for invariance principles. So for random walk, Mala, and HMC, the scaling is of order D, and the proposal, so the proposal variance, because HMC you also essentially that has to do with the time step where you're using your discretization. So the proposal variance in each of these cases, d to the minus 1, d to the minus a third, d to the minus a quarter. I think these could be the standard deviations. Yeah, very likely, but I'm not sure which one of the two anyways. So either that or twice that, or half of that. Okay, so in the first two cases, the limiting process is the Landgraf diffusion, and you can, and this actually suggests that the computational cost for these algorithm scales like d squared, d to the 4/3, d to the 5/4. The reason being that if you scale the variance of the proposal like 1 over d, you need roughly d steps to actually traverse kind of unit distance. So each one of those steps costs roughly d, so the cost is d squared, and ditto for the other two processes. And actually, in Kengo's, Gareth, and Joris's recent paper, there is a result that makes this, that justifies how you derive this scaling in terms of convergence of ergodic averages. So the thing you would actually compute from these algorithms, which is very interesting and actually ties things down. Okay, so what can we say about BPS? So this is a plot from the original paper by Alex, Arno, and Sebastian. It's a non-isotropic Gaussian, and this is the logarithm of the ESS per second of simulated process against the logarithm of the dimension, and the slope is actually 3/2. Okay, so the empirical evidence suggests it's d to the 3/2. Actually, I think this is also confirmed by Christoph's recent paper. So what can we say about this? All right, so so before we posted this paper, there was already a paper by Kengo, Joris, and Gareth, and they were looking at various statistics or observables for both BPS and zigzag. I think, if I'm not wrong, it was on a standard Gaussian target, but they were looking at the first coordinate, at the angular momentum, at the log density. So for the BPS, they were looking at velocities in the unit ball. They were rescaling time. Please correct me if I've got any of this wrong. So the time rescaling for BPS was d, and they were looking at for the first location component, because the different observables suggest different scalings, which could mean that depending on what you want to look at, the scaling, the cost is actually different. But with this time rescaling and with the cost of the amount of events you have to simulate, the cost of BPS that was suggested was of order d squared, at least for the location component. One of the reasons for that is that basically with unit speed, the number of events per unit time is of order 1. Okay, so zigzag is of order d for the first coordinate, but if you look at an IID target, that's not surprising, because zigzag has the amazing property that it just factorizes. So, I mean, you could technically compare this to running an IID Metropolis Hastings on an IID target, which again would have cost d, I guess. But so it's a very nice property. Also, similar to this is the local version of BPS, which again breaks up the process into different components and should also be achieving order d, but we still don't quite know what that is. Okay, so we'll focus on BPS, but we're studying actually a different regime. So I'm going to explain now the, okay, so before explaining the regime, I want to introduce this randomized HMC process, which is essentially the scaling limit we will get. So this is basically just like HMC, but we're now keeping track of it's a continuous time process. We're keeping track of the location and the velocity. And essentially, it's a piecewise deterministic version of HMC. So what you do is You've got your potential. You define a Hamiltonian like this. You simulate, you solve the Hamiltonian dynamics exactly. And and then you have a Poisson clock with constant rate lambda. And every time that clock rings, you just either partially or fully refresh your velocity. Okay, so at each of those times, either you set the velocity equal to an independent Gaussian, or you can do an autoregressive, or you can do all manners of things here, anything that just essentially leaves the Gaussian distribution invariant. This is the procedure we will look at for technical reasons. Okay, so in any case, whether you do this or you refresh, should only add a constant factor, because the autoregressive process has got, so it's like a discretized version of Ornstein-Uhlenbeck, and for an IID Gaussian target, its mixing doesn't decay with the dimension. So whether you do this or you do this, you should only pick up a constant factor in terms of mixing. Okay, so we make the following assumptions. So we assume IID. We can remove this, and I'm going to mention how later on, and I'm going to give you what the conditions should look like. We have potential that goes to infinity. We have second derivatives, and we assume for technical purposes, to simplify things, bounded second derivatives. In fact, you can have polynomial growth in U, but then you'd have to do a kth order Taylor expansion and have kth order bounded derivatives. Okay, and then we assume something like this. Okay, so the result is the following. So you initialize BPS with Gaussian velocities from stationarity. You look at any finite number of location and corresponding momentum components. So you want to look at both of them. And then the scaling limit is the randomized Hamiltonian Monte Carlo process, which I introduced in the previous slide. So there's no time rescaling. We consider standard Gaussian velocity, which has norm, which scales like root d compared to norm 1 if you look at it on the unit sphere. And we look at both location and velocity. So I've been trying to understand how why the two results aren't contradictory, and in fact they're not. I think that if you scale back the velocities to have unit norm and you speed up time, I think you can work out the maths. It looks like the overdamped regime in the Langevin diffusion, the original Langevin diffusion, where if you do the overdamped limit, it's like you're introducing friction. It takes you back to a Langevin diffusion, looking at just the location component. The reason is that by doing this, essentially the velocity component mixes at a much faster scale than the location, and essentially just contributes it contributes on average, so it becomes just Gaussian noise. Okay, so what can we do about the IID assumption? So technically, what you could do is assume you have a sample from the distribution. This is not the joint distribution. This is just the marginal that we're interested in sampling from, so e to the minus u. V is from a standard Gaussian target, and the two are independent. If you look at the self-normalized inner product between those two things, and you condition on any number of components you want to look at, that should have a Gaussian limit. Now, in the IID case, essentially this is a sum of derivatives of u at the independent components multiplied by the VIs. So this always has variance 1, so you can compute the conditional variance very easily, and then it's always 1. But this could very well hold for things like, so if the target is the distribution of a state space model, let's say, or something that has weak dependence, then the u's here would look like U statistics. So they would depend potentially on 2 components or maybe 4 components in a spatial model. In any case, so this is actually, you can have things like this under various weak dependence conditions. Again, the dependence matrix will have to be sparse. So if the dependence matrix is not sparse, then things may look completely different. The potential can grow polynomially, and again, we can look at any finite number of coordinates. Of course, we just look at just one. Okay, so that's the scaling result. Now, we need to think about what this is saying about BPS. We haven't rescaled time. The number of events with a Gaussian velocity scales like the square root of d. Each event costs roughly d to simulate, so potentially it's saying that the scaling is of order d to the 3/2. Now, the problem in extending the reasoning, at least the problem for me in extending the reasoning from other results, is that the limiting process is completely different. So when you have different algorithms with the same scaling limit, then you sort of have a benchmark to compare. And at least we know that Langevin diffusions mix super well, and their mixing doesn't depend on the under some assumptions, doesn't depend on the dimension of the target, and so on and so forth. So before this actually can serve as kind of a benchmark, we need to understand that the mixing of this guy isn't actually deteriorating. Then the reason for this would be that if we're looking at this object and then in fact it turns out that this actually doesn't mix, then we need to factor the mixing of the scaling process into the cost we're calculating. But if the scaling limit actually mixes well, we can treat it as, you know, having full ESS being like kind of an independent sampler, and then we can compute the cost of actually simulating the process at the regime that is required by the scaling limit. Okay, so then the rest of the talk will be about the convergence of RHMC. So we're gonna get a dimension-free convergence rates under assumptions of the form. So we want strong low concavity and Lipschitz gradients. Okay, so first of all, there's in Burabi and Sancerna paper that I think was one of the first papers to study RHMC. They prove it's geometrically ergodic using drift and minorization. Again, like I mentioned before, this usually doesn't give you rates that stay well behaved and controlled with the dimension. And again, RHMC, just like most PDMPs, has no spectral gap. So the reason for no spectral gap is that if you write down the generator of RHMC, you will pick up the generator of, so let's say we apply it to a function of x and v. You will pick up the part of the Hamiltonian dynamics, which is given by this. So this is the potential, and here you get, if I'm not wrong, yep. And then you pick up the jump part. Okay, so I'm going to put a minus sign here because I want to write this in the form I minus S alpha, where here this guy is essentially the transition kernel of an alpha regressive AR1 process. Okay, so if you don't want to think of it like that, you can think of it as a discretization of an Ornstein-Uhlenbeck process with time step that depends on alpha. Okay, so now if you look at this thing, this is the antisymmetric part, and this is the symmetric part. Okay, now the symmetric part, this only affects the velocity. So now spectral gap for any Markov process, not just reversible, is equivalent to having an inequality of the form. So this is the Dirichlet form. And essentially it's the inner product of f times minus the generator, inner product of f and minus the generator applied at f, and this is just the L2. Okay, but you can easily work out that whenever you do something like this, this is equal to the Dirichlet form of the symmetrized part of L. So minus L plus minus L transpose adjoint in L2 applied to F. Okay? So this is the symmetric part. So for our HMC, essentially what you'd see here is f I minus s alpha, maybe lambda here applied to f. Okay? Now, what we want to do is we want to show that this is more than some constant times the variance of f. Okay? If we didn't have the location component, then this would be true because we know that Ornstein-Uhlenbeck process has a spectral gap. Okay? But by introducing the location component, you can have a function here which only depends on the location, or maybe has some kind of symmetry with respect to the velocity, and for all of those functions, this thing will be 0. Of course, the variance is not 0. So you can never have a spectral gap because the only constant that can satisfy this inequality is 0. Which means that if you look at inequalities of the form PTF less than or equal to variance of f times e to the minus alpha t, the only constant that can satisfy this must be 0. Okay, so now this is the pickle with this processes. Now this is a very well-known problem in the study of Fokker-Planck equations. So the Fokker-Planck equation is just the backwards Kolmogorov equation for the underdamped Langevin diffusion or the standard Langevin diffusion. And that's also a kinetic model, so the location moves according to the velocity. And again, for exactly the same reasons, if you compute the symmetric part, it doesn't actually depend on the velocity at all. It just, the effect of that thing completely cancels out. And
so good question. Can you, so here f is a function of x or e or both?
So this should hold for functions of everything. Yeah, so if it doesn't, if there is at least one, well, okay, so first of all, f must have expectation 0, okay? So it cannot be a constant, because then it's always 0. But you have to look at all the non-constant functions. If it fails for one non-constant function, then that's it. You don't have a spectral gap.
Because, I mean, sometimes you want this one to, for x to converge, right? I mean, because like e is, you added this.
Yeah, but the problem is you cannot just focus on x, because when you look at how the function propagates, so let's say you take a function just of x, and then you look at its expectation after time t, it will also depend on v. Yeah, so if essentially if you could take the space of functions that depend just on x, and it was closed with respect to the semigroup, so if the semigroup mapped that function back to that space of functions back to itself, then you could, but it doesn't. In general, it maps it back to functions that depend on both x and v. Okay, so the way this thing was dealt with has been dubbed hypercoercivity. Coercive would mean that you have a spectral gap. Hypercoercive is the new bag of tricks that essentially was introduced by Neer and Helfer. And it was wrapped up in a very nice way by Villani in his 2009 paper, and he put it in a kind of more general framework and explained what's the algebra behind it. So the idea is that we forget about L2 for now. L2 may come back into the picture at the very end of the calculation. We work with a different norm, okay? So essentially the trick is we change the norm. So the norm we will work with is the Sobolev norm, on the weighted Sobolev norm on our space. So essentially you take the L2 norm, you add the L2 norm of the x derivative and the L2 norm of the v derivative. And then we aim to prove something of this form, okay? We aim to prove exponential convergence in this direction. Now, they were studying the Fokker-Planck equation, so they were actually studying convergence of densities, of transition densities to equilibrium. But you can actually take the dual approach and you can study convergence of expectations of functionals after time t. Now, in the Fokker-Planck equation, you can use regularization to get actually L2 bound. So you can get an equation, an inequality of this form, okay? So this is actually quite nice, right? So, but look at the difference between this and that thing over there. So the difference is the constant, Of course, the constant has to be more than 1, because if it was less than 1, this would also hold. But there's another funny thing, is that this is only possible if this is the L2 norm. This is unique to non-reversible processes. If the process was reversible, if you could get something like this, it would automatically imply the existence of a spectral gap. There's a very nice argument in the paper by Martin Hare, Andrew Stewart, and Sebastian Vollmer. Essentially, it also holds not just for for reversible, also for anything whose generator admits a spectral decomposition. So anything that has a normal generator. It's a very nice kind of tensorization trick where essentially you take the constant and you take the constant and you make it, you send it to 1. So it's very nice. So the only possibility for this without having a spectral gap is for non-reversible process. Okay, so I'm going to tell you what we did. So this is the metric we introduced. So we look at the norm. So we look at the v derivative, we look at the x derivative, and we subtract the inner product of the x and the v term. So I will call B essentially the Liouville operator, which is the generator of the Hamiltonian part, and this is our assumption. Okay? Now this is the result. So here you can see the refreshment we're actually proposing and the rate we get, and essentially what you get in terms of our modified norm. So is this convergence rate, okay? Now this norm, you can choose the constants in such a way that it is equivalent to the Sobolev norm, okay? So, so in the end, basically what you get is that you can estimate the asymptotic variance of your function as long as it's got square integrable derivatives by essentially this constant times the integral of this thing, so it will just depend on u. Okay, so we get a very nice formula for the asymptotic variance. Okay, so I think actually there's so hypercoercivity has been used in this context before. There's a paper by Dolbo, Clement Moore, and another person whose name I don't remember in 2015. They look at RHMC. They use a different metric. And actually, this was the approach that was used by Christoph Durmus, Nusken, and Roussel to do the very general stuff and amazing stuff that they did. So we actually we went for a kind of more elementary approach by working directly with the metric. But the nice thing about this is that you actually see exactly what's happening. So when you work out the calculations for these terms, you see exactly what is gaining you traction and what's giving you the contraction rate. And I'll try and explain now. So let's say you look at this norm, okay? So essentially we were looking at things like dx ptf, dx ptf, VPTF, DVPTF, okay, and the cross term, DXPTF, DVPTF. So when you analyze this term, so we want to compute derivatives, time derivatives of these things. So whenever you do something like this, essentially you will pick up the generator with a 2. So what this will look like is DVPTF, DV minus the generator PTF, okay? So this is the derivative with respect to V. Now, if you analyze these terms, you will get components of the form, let's say, grad X. So I'll replace PTF by H, but the time dependence will always be implicit. So you compute the inner product of the v derivative of this function and the v derivative of the function with the generator applied to it, and you will pick up terms that involve grad VH, S grad VH, okay? Now, S alpha is that thing over there, okay? So we know this is positive. We want it to be positive. We know it's positive. Actually, it's more like I minus S alpha. We know it's positive, but actually we want to lower bound it by something like the variance of H or the variance of grad V of H. But again, we're in the trouble that in the full space of functions that may depend on X or may depend on V as well, we don't actually have that, okay? So the saving grace is that you actually from the dv dv term, you pick up a grad V H squared, okay? And now you're almost there, because you no longer have the problem with this guy, but you still don't have a spectral gap because we don't know if the function even depends on V. It could just depend on X. So what the whole point is, you want to construct, using these terms, somehow the gradient with respect to X, okay? And the way you get that is from this cross term. So if you differentiate this cross term, you get lots of useless things, but you also get this guy. Now, if you add these two things together, this does have a spectral gap. So you can show that this thing will be, well, you can bound it below by constant times. Okay, so there's actually various operators that are missing here, but anyways. So you get the spectral gap like this. And then there is a lot of remainder terms that you somehow need to control, but it does work out. So the nice thing about this is that so we get these contraction rates and so on and so forth, and it actually did suggest a kind of Wasserstein metric to use as well. So we can get contraction in Wasserstein distance, which seems, it's a lot easier to explain. It works for a smaller class of functions, but actually proving it is very nice. And I think this kind of thing may be useful for other processes as well. And again, the distance you use has exactly the same form in principle. So you look at the norm of the location, you look at the norm of the velocity, and then you look at the norm of the cross product of the two. So here the two processes are essentially coupled. So 1 or 2 refers to which copy of the process we're looking at. And they're coupled using the same essentially refreshment times and the same refreshment random variables to do it. So, and it works great. So you get, interestingly enough, exactly the same rates. So if you plug in this lambda, you get this mu. That's the whole point. So in principle, you can play with all the parameters, so A, B, C, and with the refreshment rate, you can play with the autoregressive parameter alpha, and you can try and optimize everything. It's actually quite nasty to try and optimize it because you get a set of inequalities. And they're quadratic. They're not. Some of them are not even quadratic. They have some some places where they're not differentiable. But if you plug in these values, you get these rates. So I think we're quite happy about managing to get these. So I think that's all. Yeah. So here are some references, but hopefully I haven't forgotten anything. Yeah. Thank you very much. Yeah, I mean, yeah, if you can, so the only, I think the main thing about this is that you need to have the exact Hamiltonian. If you can do the exact Hamiltonian, then yes, you can discretize it, just look at discrete times. Because the refreshment rate is just constant, you can always do this. But I mean, that's not, you usually can't do exact Hamiltonian, so that's not the point. So this is kind of like a scaling limit and kind of a benchmark. But it looks a lot like Hamiltonian, right? So if these rates with this dependence on the condition number hold for RHMC, it's very likely they hold for HMC as well. So it's suggesting that maybe the current rates for HMC are not, don't have the optimal dependence on the condition number.